And we're live. All right. Let's do some warm-ups. I also discovered that if I rattle this thing up here, then it goes rattle, rattle, rattle in the very loudly on the video. And so I'm going to try to draw names way back here so that they will be less of a distraction to the video. Rhiannon, question A, where's the vertex?
-3, 1.
Where are the next points for a quick graph, Rhiannon?
Up 1 over 1.
Boom, over 1, up 1, both directions. So we go to here, and we go to here. Where are the next points for a quick graph, Rhiannon?
Over 2, up 4.
Boom, over 2, up 1, 2, 3, 4. We go to here, we go to here, and there's a beautiful graph, sort of my parabola. Hey, I don't have graph paper, so you know it is what it is. This still looks pretty good. I'm pretty impressed. Thank you, Rhiannon. All right, next one. Brett, where is the vertex?
-3.
2, -3. 1, 2, 1, 2, 3. Where are the next points, Brett?
Up 1 over 1.
Uh-oh. What are we missing that's different on this one than from the first one?
Oh.
So over 1 instead of up 1, how much are we going to go up?
Is it up 2?
Yeah. We got to scratch it 2. So instead of going up 1, we're going to go up 2. So we go over 1 and we go up 2. Over 1, up 2. Where's the next set of points, Brett?
Over 1, or over 2, up 8.
There you go. Over 2, and instead of 4, we're going to just multiply it by 2 and go up 8. So we got 1, 2, 3, 4, 5, 6, 7, 8. And then over here, same thing, symmetry. And beautiful, beautiful parabola. All right. Complete the square. Guys, remember when I write the words complete the square, and I very intentionally said this last week, do not get out your calculator, find the vertex, and write it in vertex form. The whole point of the complete the square is I want you to go through the process where you don't know the vertex, but you're trying to find the vertex. And it's an algebraic skill that we're doing just to help us process. Okay, the idea is, and I think I've said this to you guys before, is not that you need to know how to complete the square to get through life, but it's useful to be able to process a set of instructions where you say, okay, first I got to do this, and then I got to do that, and then I got to do that, because that's a skill that you will always be able to use. All right, let's look at completing the square. There's room here. Let's just do this. Let's just use this space. So, let's see. Avery, I got an x squared tile. How many am I putting on each side to make my square?
Just the 1.
Okay, but how many x tiles? I know you weren't here, but I'm going to sort of try to walk you through this a little bit. How many x tiles do I have?
Or you 1.
Well, I have one x squared tile, but how many x's do I have?
7. 6, -6.
So if I want to make a square, how many do you think I got to put on each side?
3.
Boom. And because they're negatives, they're going to be -3. So I've got x -3. I'm going to just draw my hand. And x -3. All right. Avery wasn't here last Tuesday, in case you guys were wondering. Yeah, yes, absolutely. In order to make this a square, I've got to fill that in. Avery, how big would you say that little square was?
9.
Exactly. So I am going to add 9 and fill in that corner. Now, Avery, I just made my equation out of balance because I just added 9 that I didn't have. What do I need to do to keep it in balance?
I don't know.
Okay.
9 times the other side?
Yes, that's a good thought. So let me write the equation out here again. I've got y equals x squared minus 6x plus 7, and I added 9 to this side. And in order to keep it in balance, I could add 9 to the other side. Actually, a couple of you did that when I was walking around talking to you. But here's the thing, I'd sort of like this to still be y equals. So what do I need to do to that 9? And I'll take a volunteer. What do I need to do with this plus 9 over here that would leave my equation as y equals instead of y plus 9 equals? Rhiannon?
Subtract 9.
Subtract 9 from both sides. Because if instead of putting a plus 9 over here, I put a minus 9 over here, do we agree that that works out exactly the same? But the advantage is my equation is still y equals, and I like my equations to be written as y equals. They're easier to work with if I do that. So you can do it either way, but then at the end of the day, you're going to have y plus 9, and then you're going to say to yourself, oh, I should subtract 9 from both sides. So this square right here consists of x squared minus 6x's and plus 9. And then I've got minus 9 plus 7 out here. So y equals, how big is that square? Luke, what are the dimensions of that square?
X squared minus 6x plus 9.
I agree with you. What's the other way to write the dimensions of that square? Length times width.
Yeah, so x minus 3
Times,
times x minus 3
and another way to write x minus 3 times x minus 3?
Squared.
Oh yeah, look at that. If I add up all the bits, I get x squared minus 6x plus 9. That's the square. But I could also say length times height. No, I don't have coronavirus. I just have a tickle in my throat.
Probably also.
So that square could also be written as x minus 3 squared. And then what do I have on the outside? Minus 9 plus 7. Luke, where's the vertex?
-3, -2.
Sure.
It's not anymore.
If I plug -3 back in right here, what do I get?
That would be positive 3.
What the other Luke said.
I haven't been talking.
At all?
No.
See, I hate this math thing because I looked at you and said Luke, and then somebody talked and I thought it was you.
I wasn't saying anything. I'm really confused.
Gotcha. So, do we agree that that needs to be positive 3? Good morning.
Good morning.
What do we got?
Avery is.
She is at 10 o'clock. Good, which means not during my class.
Wait, are we on day one schedule or day two?
Day 2. Yeah, no, we're still on day 2. I hope. They didn't, I mean, I'm assuming it's Tuesday. We would do a Monday schedule, so. Any questions about this? Okay. I believe there is a little short video on this in here. I will double check, and if there isn't, I will make sure there is one. But the little short video, I just walk through the steps. So if you get stuck, you okay? Cool. If you get stuck, you could watch the little short video again. It would remind you first do this, then do this, then do this. And if there isn't one, there will be by the end of today. I'll make sure I stick one in there so that you can go back and you can reference that. All right. That's half my goal here with all the weirdness of school. I'm trying to make this as many resources for you as possible. So take advantage of them. Don't just give up. You know, we only get 2 days, and I know that's tough, but I'm going to try to have as many resources for you as possible so that you can use those resources to make up the difference and still not be falling too far behind. So, all right. Because that's what we were working on last week. And we're going to talk about what I consider to be the most interesting part of math in general, which is modeling. And it's sort of the point of mathematics. I mean, why bother having math? Well, you have math so that you can figure stuff out. You have math so that you can figure out how much money you're going to have if you do something. You've got math so you can figure out, you know, how to build your house without just building 10 houses and the first 9 fall down. And each time you go, oh, well, I shouldn't have done that. You use math to basically allow yourself to figure out in advance, how do I do this? And then just do it once instead of a whole bunch of times. And so what they call this process is they call this mathematical modeling. And you are creating a model, and by model we mean an equation. And that equation represents the situation that you find yourself in. You can model the right angle by just using this 3, 4, 5 triangle. And what we are going to do today is we are going to look at a situation where we have a fence, and the fence is 3 feet high, and it is stuck in the ground. That's what you do with fences. And over here, no laughing at my drawing. Okay, I'm telling you in advance, do not laugh at my drawing. I'm like the worst drawer ever.
That was super good.
Yeah, but it's a super good what?
Rabbit.
Rabbit, good, thank you. Okay, I feel pretty good right about now. So what we've got here is we got a jackrabbit. Jackrabbits are these really large rabbits. They actually tend to be about yay big. You find them down in Texas and Oklahoma, that area. They're plains rabbits. And he jumps up and just clears the fence and then lands again. I'm going to erase this because we're not dealing with triangles right here. Guys, remember what shape things are when they're fly through the air? Parabolas. Exactly. If I've lost it. If I take my little squishy rubber ball and I throw it to one of you, the shape it goes through the air is going to form a parabola. Anything that's going through the air not under power forms a parabola. Rockets, baseballs, footballs, soccer balls, jackrabbits. Once he leaves the ground, he's going to go up and come down in a parabola. So the question that we have here is, can we write an equation y equals a parentheses x minus 8 squared plus k that would represent that parabola? So here's the first question I have for you. If you were looking at that picture and you were visualizing it being superimposed on a set of graphing axes, where would you put the origin and where would the vertex of that parabola be? Go ahead and give that a little bit of thought. Where would you put the origin and where would the vertex of the parabola be? Luke, where would you put the origin of your graph if you were putting that on a set of axes? The rabbit? Okay. Where's the vertex of your parabola?
Up for the fence post.
Good. Do you know the coordinates of that point?
Well, maybe.
What do you maybe think they are?
Well, the y would be 3.
And the x?
Well, you put the origin on the fence post, it would be 0.
Yeah, but you chose to put it over here, which I'm fine with. What's the x value to here?
The 4.
4. Guys, that's a perfectly acceptable answer. It turns out when you're putting something on a set of axes, you can put it anywhere you want. You could draw a set of axes and then put this parabola up here. It's sort of silly. But there are some obvious choices, and one would be to say, hey, look, the rabbit jumps from here. And he reaches his maximum height right there at the top of the fence post at 4,3. And then he lands on the ground right over here at 8,0. That's a perfectly acceptable way to draw this graph. Now, Luke actually suggested another way. He said, oh, you also could have put the origin right here. Your graph would have looked like that. And that's fine too. I actually prefer your first choice. I prefer that you put 0 where the rabbit jumps. But it doesn't really matter for the purposes of this problem. So here's the next question. Can I put that into that equation? Give that a little bit of thought. Can I put that 4,3 into that equation? And if the answer is yes, where in the equation does it go? Travis? Can I put that into this equation?
The 4 would be h and 3 would be k.
Nice. Y equals a parentheses x minus, you know what, I'm going to color code this because I can. 4 squared plus 3. I'm 2/5, I'm 2/3 of the way there. The only thing I don't know is the stretch factor. Do you think there's any chance this has a stretch factor of 1? Let's do a quick graph using a stretch factor of 1 and see what happens. I start here, I go over 1, down 1. So I'd be here, and then I go over 2, down 4. What do you think? Definitely not a stretch factor of 1, huh? I know it's going to be negative because it's got to open downwards, but I don't know what the stretch factor is. So, my next question is this. Are there any numbers that I could plug in for X and Y? Any numbers that I could plug in for X and Y that I could just take right off that graph? Think about that for just a second. Anything I could plug in for X and Y? Annie, see anything on that graph that I could use for values of X and Y? Explain. What do you mean by 3?
Guessing.
Well, you guessed for a reason, though, right?
Yeah.
What was your reasoning?
3 and 1 axis.
Okay, so I like your thought process. There's definitely a number there, but one of the things that we have to remember is that once I've drawn the graph, those numbers sort of go away, don't they? Those numbers let me draw my graph. But once I finish drawing the graph, I mean, I can erase this too, right? Once I have my graph drawn, all of the information about the setup isn't really part of the problem anymore. In the back of my mind, I'm thinking, yeah, this is all about a rabbit jumping over a fence. So the number 3 is super useful. Where do I find the number 3 on that graph, Annie? Now that I've erased all the little extraneous stuff, where do I find the number 3 on there?
Yeah.
Well, I still see a 3. Where is it?
The vertex.
The vertex. But I've already used the vertex, haven't I? I used the vertex when Travis said, hey, that's H and K. So I'm going to put a little check mark next to the vertex because I used it already. What other points do I have, Annie?
4.
But that's part of the vertex, right?
Yeah.
What other X, Y points do I know on this graph other than the 4, 3? You see any on there? 8 what?
8, 0.
8, 0. Guys, there's another point on the graph, isn't there? And this is X, Y. So my first step was plug in the vertex. My second step is going to be plug in a point XY. So let's go ahead and do that. I'm going to color code it again. Going to make this yellow, 8, 0. I've got 0. Uh-oh, gonna have an awful lot of colors. Equals A parentheses, whoops, 8 minus 4 I'm just trying to keep track of where everything came from. That's squared plus 3. And I'm going to stop color coding this now. Hey, how many unknowns in that equation? 1. Which means I can solve for A, can't I? PEMDAS, what comes first? Parentheses, what's 8 minus 4?
4.
Good. I'm not color coding anymore. 0 equals A times 4 squared plus 3. What comes next? Exponents. What's 4 squared, Annie?
16.
Boom. 0 equals A times 16 plus 3. What's the next step to solving for A? Alex? What could I do? First step to get A by itself.
Subtract 3.
Yeah. Subtract 3 from both sides. Eddie, what's the next step for solving for A?
Subtract 6.
I could subtract, but what's that?
That's A.
No, that thing right there.
Oh, times
What's the opposite of multiplied?
5.
A is equal to negative 3/16. In other words, this parabola is flatter and upside down. But we already knew that because we looked at the regular graph of a parabola and we knew that it was here, but our rabbit was here. So now I can take my A value and I can go back here and I could write y equals negative 3/16 times x minus 4 squared plus 3. Guys, that models the jumping of the rabbit. That's the equation that the rabbit travels in as he goes over that fence. I want you to put that into your graphing calculator. You can use Desmos or the graphing calculator. I want you to put that equation in. And let's take a look at the graph of this parabola. I want to know the domain and range of this parabola. Well, let's go domain. What's the minimum value of x? How far does this go to the left?
0. Oh, it goes. Infinity.
Okay. So this is going to be from negative infinity, less than x, less than, how far does it go to the right?
All the way from
Positive infinity. Now, Alex, you said something interesting just a second ago. You said stops at 0, 0. And you're right if we're talking about the rabbit, agreed? So if we want to talk about the domain of the rabbit, we would say that it starts at 0. How far does it go?
8.
To 8. Notice the difference? The equation of the parabola goes forever in both directions, but the rabbit starts at 0 and ends at 8. Because the rabbit jumps from this point. He doesn't go down here. He doesn't come bursting out of the ground, having been flying for an infinite amount of time through the earth, and then just come bursting out of the ground in a spray of dirt and grass. No, he's running along. He's not in a parabola. And all of a sudden he gets here and he thinks to himself, got to jump over that fence, and boom, off he goes, starting at 0. And he clears the fence and he lands on the ground. He doesn't go through the ground following the parabola. He stops here and then he keeps running because he's over the fence. The parabola ends. The parabola starts at 0, ends at 8. Does that make sense to everybody? Is that we're only looking at that little tiny bit of the parabola. We're not looking at the whole parabola that you're seeing in your graphing calculator. The whole parabola goes forever. The rabbit only goes from 0 to 8. And this is called a restricted domain because we're going to restrict the bit of the graph that we're only going to look at the one little bit. We're only going to look at that little bit where the rabbit's jumping, and we're going to ignore the rest of the parabola. Thank you, Alex. Let's talk about range. Isaac can't answer questions. Eddie, let's talk about this one first.
All right.
What's the lowest point on that parabola?
0.
Really?
Infinity.
Negative infinity, less than y, less than or equal to. What's the highest point on this parabola, Eddie?
3.
Agreed? The parabola tops out at 3, but goes forever, going down. Now, Eddie, let's go back to what you said when I said, what's the lowest point on the parabola? And you said 0.
Yeah.
Talking about here, aren't we?
Yeah.
Range, 0, less or equal to y, less or equal to. What's the highest point on this parabola?
3.
Notice that the highest point didn't change, but the lowest part did. We're ignoring all this stuff underground because the rabbit's not there. We've modeled this rabbit jumping with that equation. Whoops, that equation. And we said, but that's only true from 0 to 8 in the x direction and from 0 to 3 in the y direction. We cool with that? All right. Let's do another example. I'm going to leave that one up, and then I've got a couple for you to work on. So here's our new example. I fire off a little model rocket because it's fun. And my model rocket, oh, hang on a second. It's gonna have flames. Anyone ever shot those little model rockets where you put the little powder engines in them and then you got the little wire and the thing that you push the button and it ignites the engine? See a couple people nodding their heads. Those are so much fun. We used to do them all the time when we were kids. We have a little parachute built into them and it gets to the top and it goes pop and the parachute comes out, and hopefully it doesn't end up in the woods because then you don't get your rocket back. But if it doesn't end up in the woods, you can run over and grab it and put a new engine in it and repack the parachute and launch it again. Those were so much fun when I was a kid. They probably still are fun. Anyway, the rocket travels 1,500 feet and lands on the ground over here. Yeah, no, these aren't little toys that you play with in your living room and they just land on the other side of the living room. These actually had a rocket motor, a powder burn rocket motor. And when that motor went, those things off they went. and you had to work hard to keep track of them. It reaches a maximum height of 1,200 feet. Question number 1. We're going to put your graph axes, and based on where your graph axes are, identify the vertex of this parabola. Go. Where are you going to put your axes, and where's the vertex? Tyler, where are you going to put the origin?
Where the rocket starts.
I like that choice. It's a good choice. There's my graph. Tyler, do I know anything about the vertex?
You might, I don't.
Nothing?
No.
How many numbers does a vertex have to have?
2.
Good. Do I know either of them?
Yeah.
Which one?
1,200.
Is the x or the y value?
Y.
Good. So this is a bit tricky, isn't it? Because when I did the rabbit problem, I told you that he jumped from 4 feet before the fence, and that he landed 4 feet after the fence. Do we have any idea where that vertex is located on the relative to the x-axis? Halfway. We have symmetry on parabolas. All parabolas have symmetry. If we know where the vertex is, that's why when we quick graph, we go the same distance on both sides, because the vertex is always right in the middle. So Travis says, hey, look, halfway, half of 1,500 is 750. I know H and K. So I can write the equation y equals a parentheses x minus 750 squared plus 1,200. Do I know any more points? Do I know another point that I could plug in for x and y? Remember, step 2. Step 1 was plug in the vertex. Step 2, plug in another point. Brett, where's another point on my graph?
You want to find out A?
But remember, I need an x and a y value. I'm not ready to find out a.
So 1,500, 0.
I've got 1,500 comma 0 over here,
And then 0, 0.
and then 0, 0 on the other side. Doesn't really matter which one I do. It's going to give me the same answer either way. So let's just plug this in. 0 equals a times 1,500 minus 750 squared plus 1,200. All right, here we go. PEMDAS. Mr. Van Rye.
You're gonna do what's in the parentheses first?
Good. What's 1,500 minus 750, Luke?
Give me a second. I'll slow this. 750.
Hey, I'll give you a hint here. because that's always half. It's always going to be the same as that number right there. So you don't actually really even have to calculate it. Whatever you put in here, you're going to get that number there because it's halfway.
Okay.
Cool. Plus 1,200. Excellent. So everybody's had a turn. Here we go. Annie. PEMDAS. We did parentheses. What do we do next?
Exponents.
Exponents. Quick, Annie. What's 750 squared? Oh, really? Calculator? You don't know your 75 times tables?
No, I don't.
Oh, man. Anyone know their 75 times tables? I'm going to go up here. 0 equals A times.
Please excuse the interruption.
No.
Just a reminder that there's no homeroom today, so when the bell rings, you will be staying in first period. So no homeroom, stay in first period. Thank you.
So they interrupted us and kept us from teaching in order to tell us what we already knew. Annie, what's 750 squared?
562,000.
It's okay. That's okay.
A big number.
Yeah, but we're going to do some simplifying. Or maybe we won't need to. Avery, what's my next step in solving for A? I want to get A by itself.
You subtract 1,200.
Good. I've got negative 1,200 equals A times 562,500. What? Yeah?
Good morning, Meridian. Please
We'll
stand.
come back
for
to
the
this in
Pledge
just a
of
second.
Allegiance. I pledge
Allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all.
You may be seated. We have one announcement today, and it's if you were enrolled in ceramics last spring or last semester, please come to the art room to pick up your artwork. All artwork will be disposed by February 19th.
All right, Meridian, I have a buzzing joke for you. What do you call a bee that can't make up its mind? A maybe. Have a good day, Meridian.
Avery, did I just call on you?
Yeah.
Eddie,
Okay.
what do I do next?
Some math trick to get the answer.
It's not even a trick, though. I mean, you answered this one last time. Need to get A by itself?
Divide by,
I forgot to mute my phone. Sorry.
That's a notification sound.
What's that?
That's a notification sound.
Guys, there's A. But I got a question for you because that's a lot of huge numbers. What does a 0, 0 on the end of a number mean? What does it tell you about the number? What's it divisible by if it's got 2 zeros on the end? Can't divide by 0. Yes, it's divisible by 2 because it's an even number, but I can think of a bigger number that it's divisible by.
10.
Definitely divisible by 10. Oh, Annie, 100. Because 100 is even bigger, right? So what if I divide the top and bottom by 100? What happens to those zeros? They just go away, don't they? Oh, wow. That's much better. Because anytime you got zeros top or bottom, you can simplify and knock them off. reduce, divide by, however you want to look at it. What's 5,625 divisible by? There's some obvious ones. She said it. 5, but thanks for putting up your hand, Luke. Yeah, is 12 divisible by 5?
Yeah.
What? Who said yeah? Take it back. Exact. No, it's not. So that doesn't really help us. What is 12 divisible by?
6.
Yep. What else?
2.
Is that divisible by 2?
1.
No. What else? Yeah. So we got 1, we got 6, we got 2. What else? 12. Yeah. What else? 3. Here's the problem with 4. Goes the same as 2, right? If this isn't even, it's not divisible by 2 or 4 because it's an odd number. Is that divisible by 3? Do you know how to tell, Rhiannon?
No.
Watch this. 5 plus 6 plus 2 plus 5. What's that equal to?
18.
I'm gonna mute it any second now. Give me a second. So we got 11, 12, 13 plus 5 is 18. Is 18 divisible by 3? Then so is 5,625. Isn't that cool? That's divisible by 3, and therefore this is divisible by 3. Now, do we need to divide it by 3? No. We could just leave it like that, but it's sort of a fun trick to know is that that's actually divisible by 3. So we could simplify this to -4 over, let's see, 3 goes into 5 once, remainder 2, 3 goes into 26 8 times, remainder 2, 3 goes into 22 7 times, remainder 1, 3 goes into 5 5 times. So it's 1,875. So let's write our equation. Y equals, I don't really have room. There, I'm gonna write it up here. For our rocket, I'll write it in red. Our rocket equation, Y equals -4 over 1875, X minus 750 squared plus 1200. What's the domain of that? Volunteer? Domain of the rocket problem. Where does it start? Where does it end? In the X direction. Tyler, thoughts? Where does it start? Where does it end?
I don't know.
Well, you told me where to put the axis. Where do you start your axis?
0.
0. Where does your axis end, Tyler?
0.
Except we're talking X direction, right?
1,500.
1,500. The rocket lands at 1,500 feet. Doesn't go any further. How far does the parabola go? Forever, right? Parabolas go forever. But the rocket starts at 0, which is where Tyler launched it, and it landed at 1,500 feet. So it ends at 1,500 in the X direction. Good. Thank you, Tyler. Range. Brett?
-3 less than y, less than or equal to 1200.
So this rocket came bursting out of the ground after having flown forever, and it made a little arc, and then it smashed its way back into the ground and flew forever.
Yeah.
When I put it that way, it sounds silly, doesn't it? But when you say range -infinity to 1200, that's exactly what you're saying. is that that thing was just flying along forever and it materialized right at your launch pad just at the same time as you pushed the button, and it flew up in the air and you said, this is so cool, a rocket, and then it vanished into the earth and never to be seen again. Brett, what would you actually put for the bottom of the range since we're just talking about the rocket?
0.
Boom. Are we cool with that? Here's the thing about modeling. You're almost always going to have to put those restrictions on your domain and range, because equations go forever. Quadratics go forever. Linear functions go forever. Think about putting money in a bank account and adding $20 to it every month on payday. You put 20 bucks into your savings because you're going to save up for something. Well, if you model that with a linear function, the linear function goes to infinity. Well, theoretically, you could keep saving till infinity, but it would be difficult. But it also goes to negative infinity, doesn't it? And so it says your line, your linear model says at some point 1,000 years in the past, there was negative $1 million in my bank account. Well, that doesn't make any sense because I didn't have a bank account 1,000 years ago. And how could my bank account have had negative $1 million in it? So when we're modeling, what we say is, no. My line starts the day I walked into the bank and put in my first $20. And it only goes up from there. My rocket starts at 0, 0, goes up to a maximum height, and then ends at 1,500, 0. My jackrabbit jumps from 0, 0, goes up 3 feet in the air, and lands at 8, 0. We cool with that?